Hey, Griffin.
Hi.
Hi, how are you doing this semester?
Good, how are you?
Good.
Pretty good.
So you into trig?
I'm not sure. We're working on radians right now.
Yeah, sounds like you're into trig.
Mm-hmm.
You have some specific material you want to cover?
Yeah. I got a few problems from my homework the other night
Okay.
that I could use some help on. So, alright.
Now, are we just doing a half an hour tonight?
Yeah, I think so.
Okay.
Okay, so this first one, it says, assuming that the Earth is a sphere of radius 6,378 kilometers. What is the difference in the latitudes of Syracuse, New York, and Annapolis, Maryland, when Syracuse is 450 kilometers due north of Annapolis?
What's the question?
Um,
Oh, what are the latitudes?
yeah, what is the difference in the latitudes?
Okay. If we look at this from the side,
Mm-hmm.
in other words, we're looking at this from a satellite view. If we look at this from the side, we're looking at this measurement, this being the center of the Earth.
Mm-hmm.
And that being 450 miles. So the question is how many miles is 1 degree?
Okay.
Well, let's see. I don't do a whole lot with nautical miles, but I have a problem here very similar to that. And hold on.
It's kilometers, not miles.
Yeah, kilometers, right. But it's kilometers, not nautical kilometers.
Yeah.
Okay. Hold on a second. One 60th of a degree would be 1 nautical mile. And so we need conversion between nautical miles and kilometers. Do you happen to have that?
No, we weren't given anything like that.
Oh, I see how we're going to do this. So let me think about this for a moment. If you weren't given that, then we should be able to figure this out based on S equals R theta. In other words, S equals R theta. R is 6378. S is 450, because S is the arc length, And that's essentially what you're looking at. When I drew it from the side, I should have put a little curvature on it. In other words, here's Syracuse, here's Annapolis. So we know that we can solve for theta. In other words, theta equals 450 divided by 6378. Now the question is, that must be in degrees. Do you have a calculator?
Not with me right now.
Get mine here. Let's see. 450 divided by 6378 equals 0.07 rounded off. So this is 0.07 degrees. Or is, yeah, that's in degrees. And that's all I can say.
Okay.
In other words, what that makes the latitude and longitude, I don't know the relationship between latitude and longitude. I think it has to do with every degree is, to be honest with you, I don't know. But in other words, Syracuse is going to have some latitude, and Annapolis is going to have a lower latitude, and it's going to be based on that angle. Because all we did was just figure out that angle. How it relates to latitude and longitude, I could do a little bit of reading and see if I could. The only problem I have in my book relates nautical miles to degrees of latitude. And I don't have a conversion factor for nautical miles versus kilometers, so I can't do that conversion.
All right. I have one about angular speed here.
Okay.
If the car is moving at a rate of 65 miles per hour, and the diameter of its wheels are 2.5 feet long. And it's find the revolutions per minute the wheels are rotating, and find the angular speed of the wheels in radians per minute.
Revolutions per minute of the wheels and angular speed.
Mm-hmm.
All right. If the diameter of the wheel is 2.5, what's the circumference of it?
2.5 pi.
Yeah. So the circumference, here, let's write this right here. The circumference is 2.5 pi. So every time the car moves forward by this many feet, the wheels have turned once.
Mm-hmm.
So we need to convert 65 miles per hour by this to figure out how many times the wheels must be moving per hour in order for the car to be going 65 miles per hour.
Mm-hmm.
And they want it in revolutions per minute. So let's see. Let's see how we're going to do this. It's been a while since I've done one of these. They always start trigonometry off by doing these. Here I have a conversion method here. Let me think for a moment. If we start off with 65 miles per hour, we have to figure out how many feet that is per minute. So the first conversion, I got to come up with a series of conversions that ends up with feet per minute.
Mm-hmm.
Then I'm going to convert that feet per minute to revolutions per minute and angular speed.
Yeah.
So let's see, 65 miles, there are 5280 feet per mile. That gets rid of that. And there are 1 hour per 60 minutes. That gets rid of the hours. So now we have 65 times 5280 feet per minute is how fast the car is going.
Mm-hmm.
And we know that when the car goes 2.5 pi feet, the tires have made 1 revolution. So if I divide this by 2.5 pi feet, I get something per minute. That's 1 revolution per minute.
Oh.
In other words, that answer is going to give me let me come up with a number. 65 times 5280 divided by 2.5 divided by 3.14. What do I get here? I get 4,371.9 One moment. I'm looking at their example in this book. They had a slightly different example. They came up with the miles per hour, and they gave you everything else. So let's see. I got to work backwards. There's 2 pi radians per revolutions. We don't know the revolutions per minute. Okay, let's see. I think I can figure out how to do this. We have x revolutions per minute. Work through me here. I'm doing this backwards. Times, let's not use, let me use the dot. Times 60 minutes per 1 hour times 2 pi radians per revolution times, let's see, in my case the wheel radius was 18 inches per radian. In your case the wheel radius is 1.25 feet, which is 15 inches per radian, times 1 foot per 12 inches, times 1 mile per 5280 feet, and they came up with miles per hour. And so we came up with 65 miles per hour, and that should allow us to solve for x, the revolutions per minute.
Yeah.
And in fact, does everything cancel here? Let's see, that cancels, that cancels. The hour we end up with in the denominator, the radians cancel, the inches cancel, the feet cancel, and we end up with miles per hour. So our equation has to be x is going to be equal to 60 times 2 pi times 15 in our case, all divided by 12 times 5280. And that's going to be in revolutions per minute.
Mm-hmm.
So let me come up with that number. 60 times 2 times 3.14 times 15 equals 56, okay? Divided by 5280 divided by 12 equals 0.09. I think I came up with 0.07 the first time, didn't I? And I wasn't sure what I had. But this one appears to be 0.09 revolutions per minute, if I've done my math properly. And the second part was the angular speed, right?
Yeah, in radians per minute.
An angular speed. I hate the way they start off trigonometry with this chapter. I bet you have the same book I do, by Demana, Waits, Foley, and Kennedy.
No, I don't think so.
No? Well, it doesn't matter. This is the way they can start off trig, and it's the hardest part of trig almost, believe it or not, this opening chapter. I'm looking for angular speed. Angular speed is measured as, angular speed is revolutions per minute. What did they ask? They must have asked, what is the revolutions per minute and the angular speed, but they're the same thing.
Angular speed of the wheels in radians per minute.
Ah, in radians per minute.
So wouldn't you just multiply the 0.09 by 2 pi?
Yeah. In other words, if this is, we've got 2 pi radians per revolution. So the revolutions cancel and you end up with radians per minute. And that number is 0.56. So our answer is 0.09 revs per minute and 0.56 radians per minute. What else you got?
Let's see.
Have you gotten into your trig functions yet? Sine, cosine, and tangent?
Yeah, we just started on that today. I'm pretty solid on those. Let's see if there's anything that I have problems with.
So if I ask you the 6 trig functions of theta, you can tell me what's the sine of theta?
Sine of theta is 3 over 5.
It's 4 over 5.
Oh yeah, well, opposite, yeah. Opposite.
So ka toa. Remember that. That'll tell you the 3 primary trig functions. What's the reciprocal function to sine?
Inverse sine.
Okay, here, let me show you a way to memorize it. The reciprocal function to tangent is cotangent. That's easy enough to remember. There's only 2 others. There's a secant and there's a cosecant. So one goes with the sine and one goes with the cosine. And every pair has exactly 1 co in it. So the secant must go with the cosine and the cosecant must go with the sine. Notice that every pair has 1 co in it. So that's one way to memorize. And trig is nothing if it isn't a lot of memorization.
Yeah.
Not that you would notice it from this first chapter. But once you get into it, it's just going to be a whole lot of memorization. But knowing this stuff here is critical. Have you started the unit circle yet?
I don't think so.
How do you convert degrees to radians? How do I convert 30 degrees to radians?
Oh,
What's the conversion factor between radians and degrees?
Thought I had it written down.
It's pi over 180 or 180 over pi. Which one is it to convert this?
Pi over 180.
Right. In other words, you want the degrees to disappear, and the degrees go with the 180. So the degrees would disappear. The pi has radians attached. So that becomes pi over 6. So they're going to want you to know how to convert any degree to radians and how to convert any radians to degree. So if I have pi over 2 radians, then that conversion factor is 180 degrees over pi radians. That's equal to 90 degrees.
Yeah.
So going back and forth between radians and degrees is important. One of the reasons you tend to switch to radians once you get to trig, you'll be half in degrees, half in radians throughout trigonometry. But once you get to calculus, it all goes to radians because your derivatives of your trig functions are only work if the angles are in radians, not degrees. When you get to calculus, the derivative of the sine is the cosine, but only if it's measured in radians, not degrees. So you tend to go to radians and stay there, and don't switch back and forth anymore. What other kind of trig questions might you have here?
We can just go over one from my homework.
Okay.
So this one says ABC is an isosceles triangle. In which lowercase a equals 150 centimeters. And lowercase b and c equal 249 centimeters. And it says, determine the lengths find the size of each angle of the triangle and correct to the nearest minute.
If you had the law of sines and the law of cosines, John?
I'm not sure. I don't think so.
Probably you don't need it on this because it's isosceles. In other words, if we drop a bisector here, we know that this triangle here, we'll call this triangle 1, has dimensions of 75 and 249. So if I wanted this angle, which will be a good start for solving the angles here, what trig function will give me that angle?
Cosine.
Cosine of theta is equal to the adjacent over the hypotenuse 75 over 249. Which means by definition, okay, so let me get that number, hold on. 75 divided by 249, that's 0.30. So if cosine of theta equals 0.30, and we want to solve for theta, by definition, theta equals what? The inverse cosine of 0.30. You've had inverse trig functions?
Yeah.
Okay. In other words, what's important to realize here is that when we take the cosine of an angle, we get a number. When we take the inverse cosine of a number, we get an angle. Another way of looking at this is to solve this, I'm going to take the inverse cosine of both sides. I'm going to take the inverse cosine of the left, I'm going to take the inverse cosine of the right. When I take the inverse cosine of the cosine of theta, it just becomes theta, and I'm left with inverse cosine of 0.3. I don't have that on this little calculator, but I can go to Wolfram real quick. Yeah, it'll give it to me in both degrees and radians. This is a wonderful thing, this Wolfram alpha. It'd be nice if our graphing calculators worked like this. So that angle is 72.54 degrees. And if this angle is 72 degrees, what other angle, the way I've labeled it here, is also 72?
Angle B.
And that makes 144. This one's got to be 36.
Right.
Now, you will, before you're done, study something called the law of cosines, which would allow us to solve this even if this was like 247. In other words, even if it was not an isosceles triangle, we have the ability to solve this triangle based on three sides using something that looks like this. C squared equals A squared plus B squared minus 2AB cosine of C. That is the law of cosines. And that would allow you to solve any triangle given all three sides, whether it's isosceles or not. We were able to solve this one without this because I was able to turn it into a right triangle and know what this dimension was, because this altitude has to bisect that base because it was isosceles.
Yeah.
You've been doing trig for 2 weeks now? Or longer? Did you actually start last semester?
I don't think so.
I'm trying to figure out how far in you must be with your stuff that you've done and haven't done. There's a certain order that's necessary with trig, but I can kind of tell by the questions you're giving me. In other words, we shouldn't be using the law of cosines if you haven't gotten the law of cosines yet. I suspect you haven't if you've only been studying trig for a couple of weeks.
No, I haven't.
Okay. It's 5:30. Do you have any more you want to do? I'm happy to go as long as you need to.
No, I'm pretty solid on this stuff, I think.
Okay. I will talk to you next time, Griffin.
All right, thank you.
All right, bye-bye.